Hi, and welcome to the live stream of our presentation analyzing recent evolutions in malware loaders today. My name is Holger Unterbrink. I'm a security researcher at Syscalls, and I'm mainly focused on malware research, threat intelligence, and tool development. I'm based in Germany, and if you want to follow me on Twitter, you can find me at HITB72. With this being said, I'm handing over to Edmund.
Hello, everyone. My name is Edmund Brumaghin. I am also a security researcher with Syscalls. I typically spend my days doing malware research, threat intelligence, embedded systems research, campaign tracking, things like that. So what are we going to talk about today? Well, we'll start out with a crash course on malware loaders, what they are, how they typically work, and then we'll kind of dive into some of the common techniques that we see from a malware loader perspective as they try to evade detection. We've got 3 specific practical case studies that we wanted to walk through to kind of demonstrate these approaches in action, what they actually look like, what the infection chains look like, how the code execution flow has been designed by the adversaries. And then we'll finish up by talking about different ways that organizations can defend against these types of approaches, as well as how to hunt for malware loaders across the threat landscape. So we put this talk together because over the past several years, we've seen significant advances in the sophistication of different malware loaders that are out there. Loaders are used to bypass security measures, to bypass detection capabilities on endpoints, over networks, things like that. So we've tried to put this talk together to walk through some of the specific examples of some of the techniques that we're seeing attackers use to attempt to achieve that objective. So let's start out with a crash course on malware loaders themselves. And we'll start out by talking about kind of the life cycle of a Windows executable. So typically when you write software, when you write an application, you write it in a programming language like C or C++, and the resultant code is typically referred to as source code. When you're ready to convert that source code into something that can actually be executed on a Windows system, you'll typically use a compiler that converts that source code into machine code or binary that the machine can understand and execute appropriately. So from a reverse engineering malware analysis standpoint, when we come across PE32 files in the wild and we want to understand what they are, how they work, what they're intended for, what functionality exists within them, we'll typically open those same PE32 files in a disassembler, which takes the machine code and converts it into assembly, which are instructions that are more human readable and can allow for more efficient, more effective analysis. You'll typically see them in the form of either opcodes or mnemonics, which is what you can see on the slide there. Sometimes we're able to take the same executables and use a decompiler, which results in what is typically referred to as pseudocode, which looks a lot closer to what you would expect from a source code standpoint, and makes it even more easy for us to analyze quickly, identify code execution flow, identify the functionality present in the files, to make a determination as to, is this malware or is this a benign file? So from a PE32 execution standpoint, let's talk about what that actually looks like. So typically with an executable, you've got headers that conform to the PE file specification, and then you've got the code section, which contain the actual execution instructions, what the file is going to do when you execute it on a Windows system. And the first execution instruction is located at what is typically referred to as the original entry point. This is what tells the operating system where to go to begin executing the application that just executed. So as malware authors have worked to evade detection capabilities, they've developed packers and cryptors and different types of technologies where they can take the original executable, the original malware file that they've created, that they've compiled from source, and they can encrypt the contents of the code section of that executable so that static analysis of the file is much, much more difficult. Instead of seeing the actual execution instructions, different strings, different artifacts that may indicate what the executable is going to do, all of those contents have been encrypted. And they'll typically append a decryptor code to the end of the executable itself, and that decryptor code is responsible for taking the encrypted data, decrypting it, storing it in memory, and then jumping to that code to begin the actual execution. And so what this results in is on a disk or a file system, all you see are the encrypted contents, and it's not until the executable is launched in memory that the decryption process takes place. They can allocate the memory, they can decrypt and put the code there, and then jump to that code to begin the execution process. So the reality is, it's not always that simple nowadays. Loaders have gotten much, much more sophisticated, and in a lot of cases, they're actually multi-stage in that decryption deobfuscation process. So instead of there just being a single blob of encrypted code with a decryptor stub that runs, decrypts the contents, and then jumps over to execute it, nowadays you've sometimes got multiple stages of encrypted blobs, and in a lot of cases, during the execution process or the execution phase, the original executable is actually reaching out to an attacker-controlled server to pull down more data to store in memory to facilitate the actual execution of the malware. So it's gotten a lot more sophisticated over the last several years, and as a result, it's become a lot more difficult to analyze certain malware families. So from a PE file format itself, one of the things that I wanted to point out is, there are a lot of different sections within the PE file format. You've got headers, you've got the DOS stub, you've got the PE file header, you've got optional headers that can be included, and then you've got the section table that defines the different sections within the executable. And each of the sections is responsible for, different elements of the overall PE file execution. But I wanted to specifically point out the resource section, or RSRC. So these are typically used to store the different resources that the PE file will attempt to leverage. So icons, fonts, things like that. But one of the things that we see on a regular basis is that malware authors will often hide some of their malicious code inside of the resource section of the executable itself. So I'll pass it over to Holger to talk through some of the more common techniques that we've seen across the threat landscape recently.
So you have seen that the major parts of the file are encrypted, which means they are pretty useless for us for any kind of signature writing. Every time the sample is getting repacked, these sections will look completely different. And even this little unencrypted code stub, the decryptor stage 1, which is in charge for unpacking the second stage, even that one will be reorganized and rewritten from a good packer every time the sample is repacked. Unfortunately, in assembler, you have so many different options to create exactly the same kind of functionality with completely different instructions that it is easy for a packer to change the bytes totally in this decryptor stage 1. So, for example, it could add useless instructions in between of your original code, or it could just create spaghetti code by reordering the certain functions and jumping back and forth between them. It can easily obfuscate the calls and jumps by calculating the destination addresses at runtime. Or it can just easily substitute instructions. It doesn't matter if you use a jump function address or if you're using a push return. At the end, it is jumping to a certain address and doing exactly the same like before. But from a binary perspective, it looks completely different. So with a static signature, which is looking for a certain byte, we are not detecting any future malware which was repacked with the packer. The only exception of that is if the packer is making any kind of mistakes. So, for example, if it leaves certain constants in the decryptor stage, or if it is not encrypting strings inside of the decryptor stage 1, then we are able to write a signature which is likely also matching future versions of the malware. So this means that the security industry had to come up with something better than just pattern-based matching signatures. And they came up with behavior-based detection systems, which are working pretty much like you can see here on the slide. They are monitoring the API calls between the application and the operating system. And if they are seeing certain API calls in a certain order and in a certain time window, then they have a pretty good idea about what the application is trying to do. So in this case, for example, doing a DLL injection. Unfortunately, we have much more than just magic below the Win32 API in real-world operating systems. So these underlying operating structures and functions are also quite well documented meanwhile. A lot of reverse engineers looked at it, and you can buy books about it which are documenting it, etc., etc. So Malware Autos doesn't have it too hard to write code which is jumping over the Win32 API and accessing the native API, for example, directly, or sometimes even triggering system calls directly. If we are talking about these kind of things, of course, they are mainly done because of bypassing behavior-based detection systems. To be fair, behavior-based detection systems also have seen a kind of evolution. And meanwhile, they are not only looking anymore only for the Win32 API, they are also looking at other points in the operating system to detect malicious behavior. But nevertheless, if you are mixing these different layers in a smart way as a malware author, you still have a chance of bypassing these behavior-based systems. And if you are triggering system calls directly, of course, that means that you have to do all the work which the operating system APIs are usually doing. But as I mentioned before, this is quite well documented these days. And if we are talking about a system call, it's not that complicated. Of course, you have to prepare the stack, the arguments, and a couple of operating system stuff, but then you just have to move a service table index to the EAX register and execute the syscall. And with this, the syscall gets executed, which is switching the processor into kernel mode, and the processor finds the system call dispatcher over the L-star MSR. Then the system call dispatcher gets executed and looks into the service table, finds the service table index, the 5 in our case, finds the corresponding kernel mode function, the write file function here, and then we are in kernel mode, and the function can finally access the hardware and write the files to disk, or the byte or the data to disk. This is how a system call works, and later on we will see a real-world malware, which is actually mixing all these different layers and also using system calls to hide their tracks. If you're interested in how these system calls are exactly working, this is for your reference, just a snapshot of a Win debugger session, which is moving through the whole flow of an API call. So you can do that at home on your own. Besides of just mixing the different layers of APIs and system calls in your malware sample, of course people can do much more. They can also obfuscate API calls, for example, by calling the API indirectly. They can use, for example, functions like call Windows procedure, which are executing pretty much any code you are handing over to it. And they can hand over the API call address to this function, and with this they are indirectly executing that. Later on we will see a real-world example of that. Or they can build or rebuild API code and execute certain instructions on their own, and then just jump to an offset of the API to bypass the original entry point of the API, which might get monitored by an behavior-based detection software. And there are probably a myriad of other techniques how you can additionally obfuscate API calls. This means that behavior-based detection systems are still working quite well, and they are still detecting a lot of things, but on the other hand, they are also not the silver bullet. If the malware author knows what they are doing, then you have a good chance to bypass also these behavior-based systems. Beside of what I have mentioned so far, of course, today's malware also adds a couple of anti-analyzing techniques to the samples. It is usually coming with a bunch of virtual machine detection techniques and sandbox detection techniques, and you can probably do an own presentation about that. Then they're usually adding a bunch of anti-reversing technology to it. So, for example, that it makes it more difficult to disassemble the actual malware, or to run it in a debugger. And if you're interested in these kind of things on a low-level base, I can heavily recommend you this Ultimate Anti-Reversing reference, which is not really new, but it comes with a pretty nice collection of different bypassing techniques. So what we have seen so far is pretty much what malware is doing since the last 10-15 years at least. What has changed maybe in the last 4 or 5 years is that they are more and more moving away from plain cryptors or loaders, plain cryptors to some kind of what we are calling malware loaders. Yeah, they are not executing the final malware inside of the Cryptor or packer process. They are injecting finally the final malware into a foreign legit process. Yeah? They are picking a legit process which is quite common and often executed on systems like recasm.exe, and they are loading it to memory. They are freezing it. They are loading it actually in a suspended state. And once they have injected the malicious code, they are resuming the thread, and then the malware is getting executed in the context in memory, in the context of this legit process, which makes it, of course, less suspicious. If you're looking at the process list, you're just seeing this legit executable, and you're not seeing a foreign process which you have never seen before. You're not seeing this original Cryptor process anymore. This is hidden somewhere on the hard drive, but it is not in your process list. So even if you're doing an offline scan of that box, you will probably not detect it because everything inside of this loader is encrypted. And as long as the loader is not known by the antivirus system will probably not detect it. And with this technique, you can even hide known malware like known information stealers like Agent Tesla or something like that pretty easily inside of legit applications. And it makes it much harder, again, for behavior-based systems, for anti-malware systems, to detect the whole thing. If we are talking about today's malware, these different stages which we have talked about inside of cryptors or packers, they are also usually distributed over different stages with different scripting languages, with different programming languages, like you can see here on that slide. So this is a threat which we have investigated last year, and it comes in via an email. The email includes an attachment with an executable, which is just preparing the malware. It is not doing too much malicious things or suspicious things which would lead to a detection. It is just creating three registry. It is just creating 3 registry keys, which you can see here on the right-hand side. And it is dropping an HDA loader. The HDA loader is also a pretty small HTML application, which is just reading at the end this first registry key if it gets executed. But this original executable is not directly executing the HDA loader. It is just making it persistent by adding it to the current version run registry key. And then it is just exiting. It is not doing anything further. So the malware is not yet running on the box. Only if the victim is restarting the PC, of course, the HA loader gets executed and the malware infection process starts. So this HA loader loads the first stage, this little J script, which is stored in the LVT4 and so on registry key. Then this one loads and launches the Powershell script, which is then finally unpacking the final malware, which is stored in the 3rd registry key, and injects it into a legit process. So the whole infection process is distributed over a couple of different technologies, which makes it again more difficult to detect it. Of course, these scripts, which are usually used in today's malware, are also heavily obfuscated. So by just looking at them, you probably get no idea about what they are doing. You first have to deobfuscate them. And only after deobfuscation, you have the idea what the malware author is actually going for. Okay, that should be enough for the basics for now. Let's look into case study 1. Case study 1 is actually a malware loader using Heaven's Gate and a couple of other obfuscation techniques to fly under the radar. And we will have a look on the next slides how that exactly works. The malware loader itself was quite popular last year. It was used in a couple of different malware campaigns, dropping different malware families, from Ramcos to Hawkeye, Lokibot, Dark Comet, and several other ones. From a low-level perspective, the infection chain looked like you can see here on the slide. First of all, the loader tried to resolve a couple of API calls, which were necessary to unpack the second stage. The second stage was stored in the .data section of the PE file, and after unpacking and decoding it, it was jumping to this section, executing it, and doing a couple of anti-debugging and anti-analyzing checks. If these checks didn't find anything, it finally loaded two resources from the UDX and the SSC resource in the PE header. The UDX resource is actually the encrypted version of the configuration, which is necessary to unpack the final malware and parts of the configuration of the final malware. And the SSC one is the final malware in an encrypted form. So after decoding the configuration, it made itself persistent by copying itself to the app data folder and then creating a startup link pointing to itself. So the next time the PC gets rebooted, the whole infection process starts from scratch. After decoding the final malware, which was stored in the SSC resource, it is injecting it in memory into the recasm.exe process. And after this injection was successful, it was also capable of protecting the malware code so that it was not easily be dumpable by the common reverse engineering tools. And then finally the loader exited. Okay, so let's look at these different functions at the disassembler. So the first one, where they are trying to resolve API functions by CSC, looks like this. They are handing over the corresponding checksum for the API call which they are looking for. Like in this example, the get console window. They are loading the name of the library where this API call is in. And then they are calling this find API function by CSC32. That one loads the API, in this case the kernel 32 DLL, and is then passing through the PE header image in memory of this DLL. Then it is trying to find the export table of the DLL, where all the names are stored, which API calls this library is supporting. So after it has found the export table, it is iterating through all these API function names and is feeding them to a CSC32 algorithm. So it is calculating a checksum for each of these function names, and then it is comparing this checksum with the checksum which was handed over to the function. If they are both matching, they have found the API call which they are looking for, and then they are returning the address and storing it in a local variable so that it can be called directly from all over the rest of the sample. Then they are decoding the second stage by reading the .data section from the PE file, decoding it, and then jumping to this code via the call EAX instruction. The second stage is actually a little bit more complex than the first one. They are not using a well-known algorithm like checksum here to resolve the API calls. They have created their own hashing algorithm to do that, and this 7554 and so on is actually the hash value for virtual alloc in this custom hash value. They have created a function, this one which we have called exec_function here in the screenshot, which is used to execute every or almost every API call. They can hand over the different arguments for this API call, like you can see here in the screenshot, the 4 arguments which you can see here on the screen for virtual alloc. And then they are handing over this hash value, and the exec function one is using a similar technique like we have seen before to find the actual API call. But after it has found the API call, it is not directly executing it. It is using the call windows procedure trick. The call windows procedure trick is actually also used by a couple of malware scripts to execute shellcode, because the call windows procedure API function is taking a function pointer as a first argument, which is then later on, when this API is executed, then this function which you handed over to call windows procedure is then directly executed. And you can even hand over arguments to this function via the other parameters of call windows procedure. So this is a nice trick to indirectly call the actual API function which you want to call. The advantage of that is that if you're looking into a sandbox system, for example, and the sandbox system is not able to resolve this indirection, you will only see these call windows procedure API calls, but you will not see the actual API call like virtual alloc, which was actually called, or write file, or whatever the malware wants to execute via this indirect call windows procedure function. And with this, of course, all the behavior-based detection stuff doesn't work in these sandbox systems. They are also mixing heavily original Win32 API function calls with calls directly to the native API, like we have discussed before. And they are also even using certain syscalls to execute them directly. To execute these system calls, they have a function which we have called find syscall number by CRC, and it is actually doing exactly that. It is looking up the corresponding CRC number by passing through these internal operating system structures to find the corresponding syscall number. Like in this case, they are using the hash value, the checksum value for NT-close, and if they find it, they return the corresponding syscall number for NT-close. Then they are handing over the system call number to the sysenter wrapper, and this system enter wrapper function is then checking which version of the operating system this loader is running on, if it is a 32-bit version, if it is a 64-bit version, and depending on the operating system version, it is either using the sysenter instruction to execute the system call, or it is using the syscall instruction to finally trigger the system call. Before I'm going into the next section and explaining how they are using Heaven's Gate, I would like to do a quick refresher how actually the WoW64 subsystem works on Windows. You all know that you can execute 32-bit applications on 64-bit Windows PCs, and the way it works is by loading a couple of WoW64 subsystem DLLs into the process space. They are doing the translation between the 64 and the 32-bit world. The whole process works like you can see here on the right-hand side. First of all, the common 64-bit NTDLL is loaded into the process space. Then the process is initialized, but then the WoW 64-bit subsystem is loaded, and then a 32-bit NTDLL version is additionally loaded into the process space. The reason for that is, of course, the 32-bit code of the application will only be able to execute 32-bit API calls. So it needs the 32-bit NTDLL for that. And then the Valve system does the translation to the 64-bit world. And then finally, the 64-bit NTDLL can trigger the final system call. I don't want to go into too much detail about how Heaven's Gate exactly works, so I'm just giving you the basics here. You have to prepare the stack, of course, so you have to prepare a couple of settings and arguments, but then everything you have to do is to switch the code segment and to switch the processor into the 64-bit world and jump to 64-bit code. You can do that in a couple of different ways. The way the malware authors have implemented here in this loader is like you can see on the screenshot. First of all, they are pushing the 33 to the stack. Then they are doing the call +5 trick, which is pushing the address of the next instruction to the stack. In our case, this is the 419D59. And then they are adding 5 to this value. So we are ending up with the address 419D5E on the stack. So we have two values on the stack, the 33 and the 419D5E. The 459D5E is actually pointing to the 64-bit code, like you can see here on the bottom of this screenshot. And then finally, after we have prepared the stack, we can execute the returnF function, which is a far jump and which is reading these two values from the stack. So it is taking the 419D5E as the destination address for the next instruction it is supposed to execute, and it is using the 33 to move it into the CS register, which is telling the CPU that we are now in the 64-bit world, which means that the next instruction at 5E will be now interpreted by the CPU as a 64-bit code and as a 64-bit instruction. The problem with that is what you can see here on the screenshot. A lot of assemblers and debuggers are not able to recognize that. Same applies for certain analyzing systems which are emulating code, for example. They are not prepared for recognizing this 32 to 64-bit change in the middle of the code. And they are getting confused by that. The only debugger, or one of the debuggers which is actually able to follow this code is the good old Win debugger. But again, there are a lot of other tools which are getting confused by these switches. So this is again another obfuscation technique, and you can see here in the disassembler, for example, that IDA is not able to decode these bytes after the 5D, because this is only able to interpret bytes in the 32-bit world, or you have to load the 64-bit version of IDA and then you can interpret the rest of the code. So again, the code is even more obfuscated than it was before. Additionally, they are adding a couple of anti-debugging and anti-analyzing checks all over the code. They have, for example, distributed this scan process list function, which is executed from time to time, and which is scanning through the process list, like the name says. And if it finds certain analyzing tools or certain antivirus tools, then it is just exiting, and the loader is not doing anything. So after it has verified that it is not getting debugged or analyzed, it is then starting with loading this SSC resource, and it is proceeding with decrypting the final malware and then finally injecting it into the regasm process. In between, of course, it has loaded the regasm process, but I don't want to go into too much details here. Okay, that's it from my side. With this, I'm handing over to my colleague Edmund again.
Thank you. So the second case study that we wanted to walk through was a pretty interesting one. It featured a multi-stage infection chain and leveraged two different loading capabilities. So the first stage loader was a PE32 based loader, and the second was written in PowerShell and was responsible for determining what malware payloads to drop on the system based on the configuration of the system as well as the privilege rights of the user. It could be used to drop a variety of different types of malware on the system based on what the attacker was interested in loading onto the system at any given point in time. So this was discovered when analyzing telemetry data, looking at PowerShell invocations that made use of the ENC or encoded command syntax within PowerShell to load base64 encoded PowerShell commands for the system to execute. This is a pretty common way that malware will typically attempt to obfuscate the contents of the PowerShell instructions that the attacker would like to execute. So they'll base64 encode it and then pass it to PowerShell using the ENC flag. In this particular case, we discovered a pretty interesting example where the PowerShell that was executed once it was deobfuscated was responsible for disabling the Windows Defender subsystem on Windows systems, as well as disabling Windows Update before downloading additional malicious contents to execute from GitHub. So when we started to dig into this, what we discovered was that this was a multi-stage infection process that was pretty interesting. So it started out with a zip archive. Inside of the zip archive was an ISO disk image. Inside of the ISO disk image was the PE32 based loader that was responsible for deobfuscating and then kicking off a secondary loader that was written in PowerShell. So the PowerShell would operate on infected systems, and it was responsible for analyzing the system, determining what sort of parameters it was running within before making a decision as to what additional malware payloads it should deploy on the system. So it had the capability of deploying cryptocurrency mining malware, an information stealer, several remote access trojans, as well as a clipboard stealer, which I'll talk about in a little bit. So the executable-based loader was pretty interesting. Like I said, its primary responsibility was deobfuscating and executing the PowerShell second stage loader. It had several interesting pieces of functionality. One of the things that it could do was it had functions that were designed to evade detection capabilities on endpoints. So a lot of times, detection of malware is done based on the calling of specific Windows APIs in specific orders. You'll see APIs that get called in a specific order, and that's usually an indication that something malicious is going on. So in an attempt to evade this sort of a detection capability, this particular loader would make calls to Windows APIs in a pseudo-random order to try to evade that sort of detection capability. One of the other interesting things that it did was it would pop up an application error that made it look as if the loader had crashed when the reality was the loading process was continuing in the background. So once the PowerShell stage of this infection process kicks off, it's responsible for querying the Windows subsystem it's operating within and trying to determine the privilege set of the user. So it checks to see if the user is part of the administrator's group. And then it makes a decision about what sorts of payloads to drop and infect the system with based on that sort of information. So some of the payloads that it would retrieve would be retrieved directly from attacker-controlled distribution servers, downloaded and executed as normal, whereas other payloads were actually loaded using RunPE, which is a custom .NET loading capability. So in this particular case, persistence on infected systems for these payloads was achieved through the use of either scheduled tasks within Windows or through new service registration within Windows. So I mentioned cryptocurrency mining malware. The one associated with this campaign was called XMRigCC. So this is an open source Monero crypto miner with command and control capabilities. We've seen this distributed since at least mid-2019. One of the interesting things is it does have anti-malware capabilities. It features updating capabilities, and it also removes additional cryptocurrency mining malware that may have infected the system previously. So if it gets installed on a system that's already been infected with cryptocurrency miners, it'll actually remove those other miners before installing itself. Once again, the way that it persists across reboots is through the use of scheduled tasks within Windows. So this malware will infect the system, and it'll begin crunching numbers, trying to generate new Monero, and it'll communicate status updates to what's called a mining pool. It's a centralized web-based location that all of the nodes in a crypto mining botnet can communicate to communicate status updates, and it also facilitates the transfer of any generated Monero to the attacker-controlled wallet. There was also a clipboard modifier. that was responsible for stealing cryptocurrency from victims. So what the clipboard modifier would do is it would constantly monitor the clipboard for different string values that may have been copied to the clipboard, and it would check them against a list of regular expressions to try to determine if the string was associated with a cryptocurrency wallet. So it had wide support for a lot of the most common cryptocurrencies out there, so Bitcoin, Dogecoin, Monero, among others. And when it detected a value had been stored in the clipboard that matched a cryptocurrency wallet, the malware would actually replace that value with an attacker-controlled wallet of the same type, so that if the victim was making a transaction using a cryptocurrency, rather than the cryptocurrency going to the intended recipient, it would actually be transmitted to the attacker's wallet. So Azerult was another payload that was being distributed in these campaigns. It's one of the most common information stealers that we see on a regular basis. It features a PHP-based admin panel and command and control infrastructure. In this particular case, communications to C2 were taking place using a static XOR encryption key. So Azerult is an information stealer. It can be used to steal credentials, cryptocurrency wallets, cookies, and other things that may be of value to the adversary. So remote access Trojans were another payload that was being distributed in these campaigns. So based on the privilege set of the user that was infected, the attacker would either drop Rimkos, a commercial remote access Trojan, or Dart VNC, both of which are very, very common. We see them distributed in pretty high quantities at any given point in time across the threat landscape. And with that, I'll pass it over to Holger to talk through case study 3.
Okay, so last case study for today, an auto IT loader. Actually, we are seeing more and more auto IT in today's malware campaigns, and the reason for that is likely that auto IT has become a really handy scripting language for malware authors. It is offering a couple of low-level functionalities, which we are seeing some of during the presentation. And it is also offering you to compile your script directly to an executable. So it is easy to distribute your malware. In this case, the malware campaign started with an email, the one which you can see here on the screen. And this email included an attachment, an RIJ archive, which had an executable file inside, which was arrival arrivalnotice.exe, and which was an UPX-packed compiled auto-IT script. Of course, the arrivalnotice.exe name corresponded to the phishing text inside of the email to trick the user to open that, thinking that it is actually an Office document and not an executable. The interesting part here is that the malware authors combined the phishing world with the executable, with the PE world. And the script had the option to extract the final payload out of the PE resource section from the arrivalnotice.executable. And after it has extracted it from the resource section out of a couple of different font entries and combined them to a big binary blob and decoded it, then they were also offering the malware author to choose into which of these legit executable he or she wants to inject the final malware. You can see here on the right bottom side in the screen that depending on the argument which is handed over to the function, the 1, 2, 3, 4, or 5, it is picking a different legit executable. Recasm, XM build, etc., etc. So we unpacked and decompiled this auto-IT script, and of course it was heavily obfuscated. So we had to write a couple of further Python scripts which were reversing this obfuscation so that we were able to read the script in clear text. After we had the original form of the script, we saw that the first thing the script was doing was a virtual machine detection check. If it found these two processes, it assumed it was either running on a VMware virtual machine or on a VBox one, and it just exited So it just did nothing. It did not infect the user. It just exited and likely assumed that it was analyzed. If these checks did not find any virtual machine, then it proceeded with decoding the encrypted final payload data. And here it had two options. Either it was able to read the encrypted version of the final payload from this local payload string, or, like I've mentioned before, it was able to extract the final payload out of the resource section. And it was doing that by combining these font entries, which you can see here, to a big binary blob, and then reversing it, like you can see here on this slide, this decoding function. It was reversing it with a string reverse command, and then it handed it over to an RC4 decoding routine. At that point, the malware authors are introducing a third technology. Besides of using the exe resource section and scripting, they also used shellcode inside of the script. And this shellcode, which you can see here in the opcode variable, is nothing else than an RC4 decoding routine. You can also see the advantage of AutoIT for an malware author. It has so many nice low-level functionalities, like the DLL call command, for example, which you can use to directly access API calls in certain DLLs. That you can pretty much do everything a malware author wants to do. You can reconstruct shellcode. You can do pretty much everything malware authors like to do to obfuscate their scripts and their executables. So in detail, they are first allocating memory here, then they are creating a couple of instructions, copying the opcode of the shellcode, and then finally they are using the DLL call address command from AutoIT to finally execute the shellcode, which is then decoding the encrypted version of the payload and then returning it to the next function in an unencrypted way. Then we have the functionality which I've mentioned earlier. Then the malware author can choose into which legit executable he wants to inject this decoded malware, the decoded final malware. The injection routine is pretty similar to the decoding routine, which we have seen before. It is also using shellcode to inject the final payload into the legit executable. So you can see here that they are first creating the shellcode and storing it in the A5 local shellcode variable. Then they are creating a couple of structures, allocating memory, and adding a couple of commands to it to make it executable in memory. And then they are doing the call address, the DLL call address command, to execute the shellcode and to hand over the payload to the shellcode. The shellcode itself is then using process hollowing to inject the final payload into the legit executable. Once that was successfully done, optionally, they can also protect this process so that it is harder to dump, for example, or to do other reverse engineering things. And that's it from a technical point of view. Unfortunately, everything which you have seen today is quite common in today's malware families. This is what we are seeing more or less every day. And every script kiddie can hire a service in the underground or get an application which is creating these kind of loaders. So you can just buy your favorite information stealer, and even if the information stealer itself is likely detected by anti-malware, you can just buy such a loader program, which is then hiding it against the common antivirus systems. And with this being said, I'm handing over to my colleague for the closing.
So what are some ways that organizations can make sure that their systems are protected against these sort of loaders? One of the most important things is making sure that your endpoint protection systems can properly identify and analyze the most common injection techniques. So we've demonstrated several ways that malware is typically using loaders to execute the infection process. It's really important to make sure that your endpoint protection systems can properly handle those sort of techniques. And make sure that you test those over time. So as new techniques are introduced, as new techniques are developed, make sure that you're testing those sort of techniques to ensure that your systems remain effective over the entire life cycle that you have them in place. Also ensure that you have robust behavioral and network detection capabilities, and that they work together to ensure that you have the greatest level of visibility and coverage across your environment. Also make sure that you do have response plans in place in case a key security technology that you employ does fail to detect something. Make sure that you are using overlapping security controls and not relying on a single point of failure, whether it's at the network layer or whether it's for behavioral detection on endpoints. So as far as hunting for loaders, so YAR signatures are super useful in terms of being able to identify related samples, being able to pivot to identify the scope of a particular malware campaign or the use of a specific loader or what malware families are making use of a specific loader. Also, behavioral characteristics associated with the unpacking and execution process are fantastic ways to identify loader activity. So if you have a sandbox or other instrumented environment, being able to take a look at the actual characteristic of what's taking place in memory, what APIs are being called, how are they being called, and other artifacts and other IOCs associated with the malware once it's done being packed and begins the full execution phase. So one of the things that we always try to do is make as much information available to the public as we can. There are a few different resources that you can use to stay up to date on the latest and greatest threat research that we're publishing at any given point in time.
Okay, something completely different before we are moving to the QA section. We are going to release Dynamic Data Resolver version 1.0 very soon. This is a reverse engineering plugin for IDA, and it is based on DynamoRio instrumentation. It is supposed to help you analyzing malware samples which are using anti-analyzing techniques. So you can dump buffers and get dynamic values from registers and memory and so on. If you're interested and if you don't want to miss the release date, you can follow me on Twitter. And if you want to see more details about it, how it looks like, you can watch the YouTube video, which you can find here on the slide on the bottom. With this, we have reached the QA section and we are opening the mic. Thanks.
Right, guys, thank you very much for your really cool talk. As it happens, there is a question. And interestingly, you answered it at like the very last slide, but maybe there is more. Because the question was if you are going to be releasing any code or tools to help with the malware analysis.
Okay, yeah, maybe I can answer that. I hope you can hear me.
Yeah,
So,
all good.
Perfect. Yeah, first of all, of course, we are releasing this DDR tool. Just follow me on Twitter. It will probably happen in the next 2 or 3 weeks. Besides of that, if the question is going for one of these malware loaders which we have shown in the presentation, feel free to DM me on Twitter if you're interested in the Python scripts which we used to deobfuscate the loader, for example, or anything like that. But we are not going to release them in public to make sure that we are not too much helping the other side.
Does anyone have anything to add to that? Or because otherwise we're done.
I think he summed it up pretty well.
Okay. Then that is all we have. Guys, thank you again very much for your talk.